Hi everybody, welcome back to Under the Integral Sign. This is going to be our third formula development using the Leibniz rule for differentiation under the integral sign. And today we aim to evaluate this integral and develop a closed form expression for it in terms of a and b, where a is a real constant and b is a positive real number. All right, so our first step, we're going to define the integral as a function of b. And we're just going to let a is just like I said in the definition, a is a real constant. Okay, so it's an arbitrary real constant, but we're defining our integral now as a function of b. All right. So our next step is to differentiate f of b with respect to b using the Leibniz rule for differentiation under the integral sign. So f prime of b is equal to the derivative with respect to b of this integral right here. And using the Leibniz rule for differentiation under the integral sign, that allows us to take this derivative inside the integral sign as a partial derivative with respect to b. And the partial with respect to b of this integrand right here is simply negative sine ax times e to the negative bx. I'm not going to be showing every step along the way. I'm sure most of you can follow this. All right, so step 3, we're going to evaluate the derivative integral. So using the standard integral result for b greater than 0, we have this. And you can solve that using integration by parts twice. All right, so we have f prime of b being equal to negative a over a squared plus b squared, because don't forget we had this negative in front of that integral right there. So there's our f prime of b, but we don't want f prime of b. We're interested in a closed form expression for f of b. So all we do now is we just integrate f prime of b to find f of b. So f of b is equal to integral f prime of b db, which is the same as negative integral a over a squared plus b squared db, because don't forget f prime of b is negative a over a squared plus b squared. And that easily evaluates using traditional techniques to negative arctangent of b over a plus c. All right, so now we need to take care of that constant of integration. So we're going to apply the boundary condition that f of b is equal to infinity is equal to 0. And what I mean by that is if we let our b approach infinity, we get 0, because let's take a look at our original integral right here. Our original integral was this, and if we let b go to negative infinity, this e to the negative bx just goes to 0. So this entire thing will evaluate to 0. And that's where that comes from. So f at b is equal to infinity is equal to 0. So if we plug in infinity into this, we know we get 0 on the other side. So that we get 0 is equal to negative arctangent of infinity over a. Now, infinity over a is just going to be infinity. So that's going to, arctangent of infinity is pi over 2. So we have c is equal to pi over 2. All right, so let's substitute that back in. And we get f of b is equal to negative arctangent b over a plus pi over 2. And using trig identities or inverse trig identities, that is the same thing as saying arctangent of a over b. All right, so we have it. That's it. This integral right here evaluates to arctangent of a over b as long as a is a real constant and b is a positive real parameter. All right, guys. So that's our third integral, or our third integral formula that we've developed using differentiation under the integral sign, aka Feynman integration. So stay tuned, and we'll see you next time.